My name is David Barrera. I'm here to present this work on behalf of my co-authors, Abdu and Paul. They're located at Carleton University, and I'm currently a postdoc at ETH Zurich. This is sort of a side project that I did with them over the past year. Okay, so secure shell. So if you've never heard of this, I'm going to get you up to speed so that you know everything you need to know to understand the rest of this work. So secure shell is a protocol that's used to perform logins to remote servers, and this can work over an unsecured network and typically is used for system administration, but there's a lot of different applications that can be built on top of SSH. So you can, for example, tunnel other protocols over this protocol. And it's sort of governed by a number of RFCs and everything from key exchange modes, transport protocol, key management, key generation, certificate management. All these things are defined in different RFCs. But it's an open standard, which means that anybody can implement their own client and server implementations. And therefore, there's a bunch of implementations for different operating systems. Pretty much every OS you can think of will have some way to use this. Very popular one, I've got a picture of it here. It's OpenSSH, which is developed by the BSD Foundation. And this is the standard one that they put on a lot of distributions. So setting up one of these things is pretty easy, even for non-technical people. You can just go in and type some simple commands, and this will get your SSH server up and running. Sometimes it's enabled by default, so if you buy something like an embedded router or something like this, they'll come with these servers enabled by default. And they're listening on TCP port 22. So okay, so that's all you need to know for SSH. But if you've heard about this and you're like, okay, well that's cool, I want to maybe manage my system remotely or do something like that. I've showed you it's pretty easy. Then what you do is you set it up, and then what you get is something that looks kind of like this. If anybody's ever looked at these logs, this might not seem too unfamiliar. Basically, there's just kind of like this flood of login attempts that just keep appearing. If you look at the date of this GIF, I took this 2 days ago on one of the servers that I have access to. So this is a pervasive, consistent problem of people trying to break into SSH servers all over the place. Okay. So these log files are kind of a nuisance because if you're trying to figure out anything about your system and you open up a log file and they're sort of looping this way with so much information, and you're trying to get any useful data out of it, it's kind of annoying to be seeing these things going through your screen. So I'm just going to, in case you've never seen one of these log files, I'm just going to break down what the contents are. So this is another screenshot from taken recently. So these logs contain a column telling you what the source IP address of that login attempt was on your server. They're also going to tell you what the timestamp was for that log file, and then what the username that the remote party attacker, adversary, whatever, tried to guess on your system. Note there are no passwords in these logs, and there's a good reason for that, because if maybe you typo your password or something, you don't want that password showing up inside your on your log files. Okay. Okay, so based on these logs, and if you look online, this is a pretty common problem for a lot of people. Sort of empirically, we know that these attacks are pretty annoying and they're very frequent. We know that root is a very targeted account. As I showed in those logs, most attempts were going towards the root username, probably because it's the most rewarding account. Once you have root X on a system, you can do a whole bunch of other different things. And the source IP addresses of these attackers are also pretty diverse. So there's no sort of rhyme or reason for why they come from a certain part of the world or a certain IP address space. They just seem to come from everywhere. And if you go online and try to figure out solutions to this problem, you'll find a lot of kind of what we call it folklore in the paper, kind of advice on how to deal with these things. And everybody has their own ideas on how to deal with this. I'm sure a lot of you have dealt with this problem and have certain ideas on how to deal with this. Some solutions have this software that monitors these log files, and then when a certain number of connections are received, then it'll add a firewall rule to your firewall to sort of block future connections from that source. So these are sort of stopgap measures that you can do. And so in this talk, what I want to go over is I want to just talk about doing some research in this space and what our objectives are. Then I'll talk about how we try to do this, and then I'm just going to give you some highlights of the research results that we found from this data. I'm going to focus on passwords given the theme of the conference. Okay. So our objective is to analyze automated SSH brute force attacks. And it's important that this automated bit, I think, is a key part of this, because there's always going to be cases of somebody targeting an organization or a user specifically, and this might be a more complex, more difficult to mitigate attack. If somebody knows something about your organization or or personally, they might be able to guess your password easier. But here, we want to focus on this sort of shotgun approach of just trying to break into everything and see what sticks. So we're trying to get these, trying to analyze these automated attacks, and we want to look at the passwords that are used in these attacks as well, to see if we can try to uncover some of the more subtle behaviors that attackers are doing. And maybe if we understand how the bad guys are operating, maybe we can propose some better defenses. Okay, so our methodology is going to be as follows. We're going to set up a bunch of SSH servers that have no valid accounts on them. Okay, so anybody who tries to log into these servers is going to fail. There's no honeypot, so we don't really want to let people log in and then see what they're doing. We just want to see what usernames and passwords they're trying. And this kind of scopes our research problem to just the timing and what passwords and usernames they're trying. So again, we're going to log the passwords as well. Then the idea is that we're going to analyze this data, and then we can solve this problem for everybody. Okay, but it turns out after we started collecting this data, we turned out to sort of uncover more and more weird things, and we weren't really able to solve this problem yet. So I'm just going to present the findings here at Passwords, and then maybe let some of you guys then go ahead and solve the problem, maybe at next year's Passwords conference. Okay. So the SSH servers were instrumented to log guest passwords. So I showed them those log files. Passwords don't show up. And there's no configuration option that you can set up on SSH to log the passwords. So there's a design choice that they made to prevent people from accidentally turning this on and then sort of violating the privacy of their users or something. So what we had to do is just modify the source code to the OpenSSH daemon, and you add a little log thing that says dump the password when you receive it. So we rebuild the daemon, and then we run this instrumented daemon on these VMs. Now we're sort of worried about ethics as well, and so we want to prevent somebody who, for example, typos an IP address from putting in their password into a system accidentally. So we want to just basically target exclusively automated attempts. So we displayed this banner prior to login, prior to requesting a username and a password, in hopes that somebody who accidentally types something in, types an IP address and it hits one of our servers, they don't end up revealing their passwords. I think this is very important. And I think if you're doing this kind of work, like, you want to try to minimize the chance that a user might accidentally, leak their password on them. Okay, so the log files, once we've instrumented the daemon, look as follows. So we see these attempts come in, and so we have the same log line logging the guessing attempt, and then with the next line is this SSH log line that shows us the root that was the username that was attempted, and then the password that was attempted. So if you look at this particular screenshot, you can see some ideas of what we're going to be seeing in these logs, which is, for example, here the attacker is always this 103.41.124.55, and they're trying all these passwords that start with the letter J, and then iterating through some dictionary. So this is the kind of intuition that we want to get from this work. Okay, so we wanted to do sort of two types of studies. So one was a long-term data collection period that lasted over a year. So we had one instrumented virtual machine running for a long period of time, and then we had 5 short-term virtual machines running over more than a 2-month period. And the reason we want to do this, we wanted to compare whether the results, whether the attempts that we observed on the small time study also applied to the long-term and vice versa. And then the 5 short-term VMs, we also distributed them across the world to see if there was any particular geographical influences of those servers as well. So the long-term VM was in Ottawa, and then we have the 5 VMs were located in San Francisco, New York, London, Amsterdam, and Singapore. And the fat penguin is in Ottawa because He collected more data than the other ones. So just to give you an overview, a feel for what kind of data we got, so we logged over this entire data collection period over all the VMs. We logged a total of 17 million, or slightly over 17 million total guessing attempts. These came from just slightly over 6,000 different source IPs located all over the world in 112 countries. We saw almost 28,000 distinct usernames, and we collected about 1.4 million distinct passwords. Okay, this is just what we saw over the whole set. In the paper, we break this down based on the different VMs and different locations. Okay. I'm going to talk about some timing analysis just to give you a feel for what you can expect to see if you set up one of these VMs yourself, and then I'll dive into the password stuff. Okay, so for timing analysis, so we have a couple of different ways of breaking this data down, but I think the highlights here are as follows. There wasn't a single day that went by where a VM saw no login attempts. Okay, so the minimum login attempts for each VM was at least 180, and we hit a maximum of 273,000 attempts in a single day. Okay, this is, perhaps I should have said this earlier, these VMs had no DNS entry anywhere. They had no forward or reverse DNS. They were not advertised anywhere. These were just fresh IP addresses, and even in that case, we were receiving all of these attempts. The Ottawa VM got hit the hardest, I think overall, and we saw that this one in 1 hour on June 14th received over 85,000 attempts in a single hour. So that's 24 login attempts per second. Okay, so these things will fill up your log files very, very quickly. The European VMs seem to receive more stable sort of rate of attempts. So they didn't have as spiky connections as the Singapore or the American VMs. So maybe there's some sort of IDS thing going on with European backbone networks, or maybe they're just more aware of what the clients in those areas are doing. But the European VMs seem to receive sort of more stable distribution, and we have those details in the paper, and you can go look at them there. Okay, so I'm going to show you some graphs here. So on the left we have the Ottawa VM. Attempts per day are plotted, and on the right we have sort of attempts per minute for the other VMs. So I'll start with the left side of the picture. So a couple of interesting points here. So the first two spikes around May and June, these ones were done by a single source IP address. So a single source hit this VM pretty hard. And the interesting thing is that these sources only did all these guesses and then went away. We never saw them again over the whole data collection period. Okay, two different sources came once, tried a whole bunch of different login attempts, that went away. They never came back. There's another spike around November, late November, and this one was a more distributed spike where about 55 different source IP addresses all participated on hitting the same source, the same destination. Sorry. So there's interesting things like this where sometimes you see you see these attacks being more distributed. Sometimes you see them being just a single IP somewhere, just doing this on their own. Now let's focus on the right side of the picture now for the short-term VMs. And so here what we're trying to see is basically we're trying to get some intuition for what's the time to the first login or guess on one of those VMs. So we saw that basically we booted all these up at the same time at 12:30, and it took 51 minutes to receive the first attempt on the New York VM, and the Singapore VM took about 4.5 hours to see the first attempt. And the behavior is actually kind of interesting. Once the VMs are discovered, we see sort of a flood of attempts come in and sort of go to the thousands of requests per minute, and then later it kind of tapers off, and then the login attempts just sort of are more persistent throughout the rest of the collection period. But basically, when they're discovered, it's like everybody swarms to try to do as many guesses as they can before I guess the admin realizes this and starts implementing some other measures. Okay. Right, and so just by doing some statistical confidence in our data, we find that if you set up a new open SSH server with 90% probability, you're going to be seeing between 6,000 and 24,000 password guessing attempts per day. Okay, this is what you should expect to see if you set up your own server somewhere. Okay, there's a lot more details in the paper about this timing stuff, and I encourage you to go take a look. All right, so for the second half, let's focus on passwords. So as a reminder, we were logging the passwords that we saw during these guessing attempts, in addition to all the normal guessing or log properties. So I'll just show you very briefly. This is what we observe as the top passwords. Now, there's been prior work in this space where they kind of come up with, these are the top passwords that you see, and I think that this is kind of cool, but I don't think it tells us very much if we just see the top passwords. We can't do very much with that. So what we did is we compared it to other leaked password data sets that we find in the wild. So for example, the RockU data set has these top passwords that I'm showing, and we saw a lot of passwords in our set that are not included in the RockU data set. And possibly this is due to SSH being sort of a more technical, more system administration thing. But one of our intuitions was that attackers would take leaked data sets and then just take these passwords and then dump them into their own word list. We don't think this is the case. We think that people who are attacking SSH servers are creating their own password lists by some other mechanism, but they're not really using the leaked password data sets from, Yahoo passwords or Ashley Madison or whatever, RockU. Okay. Okay, so some data about password length. So we saw passwords of all kinds of lengths, all the way from passwords of length 0, which basically they just tried the username and then sent us a password, all the way to passwords greater than 100 characters. Okay, so this is sort of the distribution, and here in this graph we're showing the number of passwords and the number of guesses that we saw for passwords of that length. And so these distributions kind of follow each other. The most popular lengths were 6, 7, and 8 characters, and we also saw more passwords of that length. You'll notice there's a little spike at passwords of length 32. Not sure why that is. If anybody has a 32, yeah, so maybe they're taking a hash something and dumping it in and using that as a password. We also saw passwords of over 100 characters, and this was kind of weird to us. We said, well, who would have a 100-character password? So we investigated a little bit more. What were those passwords? We found some pretty funny things, which may hint at maybe misconfiguration on the attacker side. So, I'm listing 3 different passwords here of passwords over 100 characters. And if you see what the first one is, it's like falcon, fallacy, fallible. So these are all words that start with F. And so maybe the line breaks in the password file weren't set correctly. And so he just took whatever and then tried to send us that until the buffers were full. So obviously that password is, that seems like a misconfiguration on the attacker side. And we did see a lot of hints of not a lot of sophistication on the types of passwords that were being used. So we saw a lot of errors, this seems to be an error. We also saw what looks like a Unix shadow entry being tried as the password to a system. So it's hard to say where they're getting these passwords from, but they're clearly not sanitizing their word list. They're just taking whatever they can and sending it and seeing if it sticks. So yeah. Okay, password composition. So again, as compared to the RockU data set, we have kind of a similar distribution of passwords with and without special characters as RockU, but that's about it. The rest, we have significantly more passwords that are only lowercase. We have fewer passwords that are only uppercase. And then maybe the letters and then letters followed by numbers are also pretty commonly attempted by attackers. So yeah. Not really sure what else to say about this. I mean, it's just we really strongly believe that these passwords are not related to the same type of leaked data sets that we see for some of these web leaks. We saw some passwords that were constructed as what look as URLs, and I think people who've analyzed the RockU set have also seen passwords that look like URLs. Not sure what's going on there, but they're basically trying some URL as the password. We saw about 3,000 of these URL-like passwords. Kind of weird. Okay, so password list sharing. So to gain some insight to see if attackers were maybe pooling their resources or sharing passwords amongst each other, or maybe distributing their attack, where we looked at the literature and tried to see, well, how are other people doing this? So there's a paper by Owens and Matthews in 2008 that did a similar type of analysis. And they said, okay, if a username and a password pair are seen in the same order from different sources, then we'll say that they're sort of sharing this password list. But we had significantly more passwords and significantly more usernames than they did. So we had to come up with our own methodology to try to make sense of this data. And so we came up with a visualization approach. So there's a lot of information embedded in these heat maps, but I'm going to try to break down sort of what these are. So what we did is we built per source IP dictionaries by looking at all the passwords that were seen used by a specific source. Okay, so each source has a dictionary, and because there were just too many of them, we sort of truncated them at the network boundary. So every /24, all the passwords that were seen by a host in that /24 were pulled together as a single password set, and then we put those on the X and Y axes. And the point on this heat map, the shading of that point tells us what % overlap there was between a password in one of the points on the x-axis and the point on the y-axis. Okay, so purple being 100% overlap, and we can see this sort of diagonal going from the bottom left to the top right. You would have 100% match when you compare a password list to itself, but when you're comparing two different sources, you might see a different type of shading. So I think there's a lot to see, and we spent weeks and weeks just looking at this picture and trying to find like interesting things about this picture. The paper talks about some examples, but I'm going to focus on just a couple. So if you note, there's some banding between around here. Where's my mouse? Do I have a mouse? No. Okay, I don't have a mouse. So there's a band. So at point like 1.93, 0.32, there's a white band going up and a white band going across. So white means that there's no overlap between passwords in this source's set and anything else in the set. So this source is using pretty unique password as compared to everybody else. And when we further investigated this, we found that there was 15 hosts that were using exactly 500 passwords. And what appeared to have happened is the attacker had built a big dictionary and then split it up into chunks of 500, and then given each one of these chunks to one of the sources. So they didn't have any overlap between each other, and they didn't have overlap between as compared to any other attackers in our data set. So sometimes they're showing a lot of sophistication by distributing the work this way. And then there's the most notable one is this circle on the top right, big overlap between a lot of different sources to a lot of different other sources in our set. And here what we think is happening is this is probably an attack tool that comes with a default password list, and then everybody's just sort of running it on the default configuration. And so there's something like 100 passwords in the set, and then we see them used by a bunch of different sources, about 400 different sources actually from this picture. And you can basically pick any point on the heat map and find a story about it. But this kind of shows us that passwords are not. I think the predominant orange and purple shading of this figure shows us that passwords, a large set of passwords are pretty much reused by a lot of different attackers, and then there's a few exceptions where there's some very unique passwords to certain attackers. Okay, usernames and passwords. So I'll just very briefly go through this. So most of these guesses targeted the root or admin account specifically. But 37% of source IP addresses never try to guess passwords on that set. So I think guesses that were aiming for root and admin were the noisiest, but then there was some attackers that were trying to get some low privileged accounts with more probability. We also saw guesses where the username was equal to the password, and this was a pretty common guess. And we also observed some really strange behavior of attackers re-guessing the same password on the same victim VM more than once. So about a third of all guesses were repeated guesses, which leads us to believe that attackers aren't keeping state of whether a guess succeeded or failed. And this is interesting because this means that they're basically just spamming everybody and then trying to basically re-guess over and over again. There was one case where one specific source tried the same username and password pair, this root and //001, on the same VM 1,200 times in 19 minutes. And so I don't know what they were trying to do, but obviously just keeping guessing the same username and password wasn't going to succeed, within a 19-minute period. Okay, so I'm out of time, but I do want to encourage you, if you saw anything that seems interesting from this talk, go take a look at the paper. There's a lot more analysis in there. We have username analysis, distribution of IPs within subnets. We have IP addresses as a ratio of total IP allocation per country, so we can find the most malicious countries. We have the consequences of changing your SSH daemon to a different port, which is common advice. And we have some ideas of whether that works or not. There's another cool heat map, and there's some recommendations that we can give system administrators based on the data that we observed that might be a little bit more insightful than just saying, hey, turn on public key authentication and go to town. So in that case, this might not always be a solution for everybody. Okay, so I'll take some questions. Abdu says thank you as well from Canada, and my Twitter and my email and his email. So thank you for your time.